In this video, we'll work through a one-sample t-test from beginning to end. Okay, let's go. So here's our scenario. A flu pandemic has hit the country, and we think this will lead to a change in students' performance on the GRE. Maybe scores will be lower due to the added stress, or maybe scores will be higher due to social isolation and more time to study. Assume we know that the mean GRE score in the population prior to the pandemic was 300, but we don't know the standard deviation. We'll set alpha at 0.05 and we sample 5 students who took the GRE shortly after the pandemic ended and obtained the following scores. But let's not look at the scores quite yet, okay? So in this scenario, we think that GRE scores will change following the pandemic. Now, based on all of this, which statistical tests should I perform? Well, I think I've kind of already let the cat out of the bag on that one, haven't I? We'll do a one-sample t-test. But the important point here is why. Notice that it's one sample, right? And we have a set value that we're comparing that sample to. And we have an interval scale, right? But based on all of that, we could almost do a one-sample z-test. But we're missing something. What is it? What are we missing? Notice we don't know sigma squared. That's why we can't do a one-sample z-test. Okay? Now, based on this scenario, what would be our alternative hypothesis, H1? Well, to start, we can see that it's a two-tailed hypothesis. We see that right here, right in that highlighted section. Notice we think there will be a change in performance, maybe higher or maybe lower. Now, in this example, I go on to directly say maybe lower, maybe higher. I won't always be that direct, all right? But the key is to look for exactly what the question is. Don't get tripped up by what you think the question should be or might be. Look at exactly what the question is. Now, in the simplest terms, we could say that our alternative hypothesis is mu1, the mean we expect to see in the population based on the alternative hypothesis. We could say again, mu1 is not equal to mu0, the population mean, if the null hypothesis is true. But we can be more precise than that. Again, we're predicting that the population mean is now different. But different from what? Well, we see that right here in this highlighted section. We think the mean after the pandemic will be different than 300. So 300 is the mean that we expect to see if the null hypothesis is true. If there is no difference, if there is no change, we'll see 300. 300 is our mu0 in this case. Now, we could rephrase our alternative hypothesis more precisely, therefore, as mu1 does not equal 300. In English, we could say the same thing as the mean score for students taking the GRE shortly after the end of the pandemic is not equal to 300. All right? So that's our alternative hypothesis. What would be our null hypothesis, H0 or H0? Remember, it reflects the complement of the alternative hypothesis. Between the two of them, they have to cover all possible outcomes that we may see. Well, if the alternative hypothesis, H1, is that mu1 does not equal mu0, or more precisely, that mu1 does not equal 0, does not equal 300, then the null hypothesis must be that mu1 equals mu0, or again, more precisely, that mu1 equals 300. All right? In English, we could say the null hypothesis as the mean score for students taking the GRE shortly after the end of the pandemic is equal to 300. All right, great. But notice there's even more that we know at this point. You know, we know the population average, mu, is equal to 300. That's, again, also our mu0 because we're testing whether things have changed from that historical population average. We also know our sample size, n is equal to 5, which also means that our degrees of freedom for a one-sample t-test is equal to 4. Correct, right? Remember, that's n minus 1. The degrees of freedom for the one-sample t-test is the sample size minus 1, right? We also know that our alpha is 0.05 because we stated it up front in our description of the question. Now, notice that based on all of this, we can also determine the critical t-score we need in order to reject the null hypothesis. To do that, let's quickly go to TScoreMagic and find that value. So here I've opened up TScoreMagic. I need to use the area to t-score sheet, right? Because I know the area, that's that 0.05. That's my alpha level. I know that area that I want. But what I need to do is find the t-score where 5% of the distribution is more extreme than 0.05 because it's a two-tailed test, right? So I first go and select the area to t-score sheet. Then I enter 0.05 for my area. I put that in the enter area box. And I enter 4 for my degrees of freedom into the enter the degrees of freedom box. And the results for 4 different types of areas under the t-distribution will appear. Now, remember, I want the plus or minus t-score for an extreme area of 0.05 because, again, we're doing that two-tailed test. Now, as we can see in the figure, that's this one, right? Notice the figure next to it shows me that, yes, that is the area that I want, those extreme tails. So my critical t-score, that t-score with 4 degrees of freedom beyond which lie 5% of the distribution, is plus and minus 2.7764 or 2.776 if I round to 3 decimal places. Now, visually, this corresponds to the areas A and D in this figure, right? Now, ignoring the actual t-scores for a moment, we'll reject the null if the results lie in either of these extreme tails of the distribution. Now, I like visualizing the distribution and defining where my regions of rejection are. Is it above or below or more extreme than a given t-score? It just helps me to be certain that what I want to do lines up with the t-scores that I'm pulling out of TScoreMagic or some table in the back of a book or some calculator somewhere. Now, what's really kind of cool is notice that we know all of this before we've actually even looked at our data. we already know the t-score we'll need in order to reject the null. All right, pretty nice. So let's take a look at the data and see what we find. Here are the scores for our 5 students. Student 1 scored 280, student 2 scored 290, student 3 out of 300, student 4 had 295, and student 5 had 275. Let's calculate our t-score based on those values, all right? Now, this will take a little space, so let's first clean this up, all right? We'll start by first writing down all of that information we know, mu and alpha and n and the degrees of freedom and our critical t-score. Let's then list our scores for the 5 students. To get our t, right, we're going to use these scores. But we'll need to know the sum of squares in order to calculate t. And to get the sum of squares, we're going to need the mean for the scores, right? So let's first add up all of these in order to get the sum of our scores, the sum of x. And if we do that, we find that they sum to 1,440. We then divide that by 5, our sample size, in order to get the mean, which is 288. Great. Notice again, we're dividing by n, by 5, because we want the mean of the scores. Using our mean, we now calculate the deviations from the mean by subtracting 288 from each score, which gives us 280 minus 288 is negative 8, 290 minus 288 is 2, 300 minus 288 is 12, 295 minus 288 is 7, and 275 minus 288 is negative 13. Now notice that the deviations will sum to 0. If they don't add up to 0, you must have made an error somewhere. Don't just ignore it. Don't just think, wow, that's kind of strange. Go back and find where the mistake is. The deviations will always sum to 0. All right? Now, in this case, we take a quick look. Yep, they all sum to 0. So we're so far so good. We then square these deviations from the mean, right? And we get negative 8 squared is 64, 2 squared is 4, 12 squared is 144, 7 squared is 49, negative 13 squared is 169. All those negative values disappeared as we squared them, right? And then we add up those square deviations and we get 430, which is our sum of squares. It's our sum of those square deviations. Awesome. Now, for clarity, let's copy that 430 and put it down below here, right? And we'll keep going. First, we'll use the sum of squares to calculate the variance, s squared. Remember, it's a lowercase s now because it's our inferential version, right? Now, the formula for variance is the sum of x minus x bar squared, our sum of squares, divided by n minus 1. That works out to be 430, right? We just calculated that, divided by 5 minus 1, or 4. We do 430 divided by 4, gives us 107.5. So our variance is 107.5. Nice, right? Next, let's use the variance to calculate our standard deviation. That's s, lowercase s again, because it's our inferential version. And the standard deviation is just the square root of the variance, which is the square root of 107.5, which gives us 10.368. So our standard deviation is 10.368. So far, so good. Now, also remember that the standard deviation is an estimate of how spread out our individual scores are in the population. But to calculate t, we need to know the standard error of the means, how spread out means would be based on an infinite number of different samples of 5 students from the population. Well, to do that, let's do those calculations. We abbreviate the standard error of the mean as S sub x bar. That's just a way of saying it's the standard deviation S of means x bar, which is what it is. So the standard error of the mean is equal to S, the standard deviation, divided by the square root of the sample size n. Plugging in our data, this is just 10.368 divided by the square root of 5, which gives us 4.637. That's how spread out we would expect to see different samples of 5 students, different means from samples of 5 students. Let me repeat that. That's how spread out we would expect to see the means of an infinite number of samples of 5 students for each of those samples, right? So that's the standard error of the mean. We're now ready to calculate our t-score based on that. Remember, t is equal to x bar minus mu naught divided by the standard error of the mean. In other words, the numerator is how big of a difference did I see between my sample mean and the mean I would expect if the null were true. How big is that difference, right? That's the numerator, divided by how large of a difference did I expect to see given the standard error, using the standard error as my measuring stick, right? How big of a difference did I see, divided by how big of a difference did I expect, right? The standard error is that measuring stick we're using. Well, plugging in our values, that works out to be 288 minus 300 divided by 4.637. That solves to negative 2.588. So our t-score is negative 2.588. All right. We then need to use that t-score to determine our p-value, the probability of obtaining a result as extreme or more extreme than what was observed in the direction of the alternative hypothesis. In this case, in the direction of the alternative hypothesis means that we're looking in both tails because it was a two-tailed test. So to get the p-value, let's take this t-score back to TScoreMagic and find whatever our p-value is. So here, I've opened up TScoreMagic again, but this time I'm going to the t-score to area sheet because now we know our t-score. We just want to know the area that's beyond that t-score in both of our tails. I then enter the t-score of negative 2.588 into the enter a t-score cell, and I enter my degrees of freedom of 4 into the enter the degrees of freedom cell, and I instantly get 4 areas. The area above or below a t-score of negative 2.588, and the area that's more extreme than plus or minus a t-score of 2.588, and the area that's between a plus and minus t-score of between a t-score of plus and minus 2.588. All right, you see those 4 different ways. Now, in this case, what do we want? Remember, we want the area that's more extreme than a t of negative 2.588? Well, looking at the figure, right, that's this one, right? And again, notice that the figure next to the value shows me that, yes, that's the area I want. So my p-value, the probability of obtaining a result, a t-score that's more extreme than negative 2.588, is equal to 0.0608 or 0.061, rounding to 3 decimal places. We got our p-value. Awesome. Now, we can formally write that out in statistical notation as t parenthesis 4. Remember, put the 4 degree, there are degrees of freedom in the parentheses. T parenthesis 4 equals negative 2.588 with a comma then, and p equals 0.061. So that's a formal way to write up our results in using good statistical notation. Remember to include the degrees of freedom in the parentheses, and also remember to italicize the t and the p, and it will look beautiful, just what we're supposed to get, all right? Now, based on that, what's my statistical decision? Well, given that our p is greater than 0.05, we'll fail to reject the null hypothesis, right? It's close to being statistically significant, but it's not. It's just a little bit too big, but it is what it is, so we will fail to reject the null. Now, we can translate this into a substantive conclusion, something that we could use to explain the results to someone who's never taken statistics. And we could do that by stating that the GRE scores do not appear to be impacted by the pandemic. That would be our substantive conclusion. All right, great. Now, there's one more thing I want to touch on before we wrap things up. Let's calculate our 95% confidence interval. Now, I'll use a 95% confidence interval so that it lines up with our alpha of 0.05. To do that, first, what's the formula for the 95% confidence interval? Well, it's just x bar plus and minus the critical t-score times the standard error of the mean. Now, note that we're using x bar, not mu. The confidence interval bounds our observed mean, not the population mean or the null hypothesis mean, the observed mean x bar. It also is using the critical t-score for an alpha of 0.04, not the observed t-score. Use the critical t-score. Both of these are where I'll sometimes see students use the wrong value and get the wrong answer. So avoid that problem, all right? Now, given that, we've got the formula, let's plug and chug. We substitute in our values and get the 95% confidence interval is equal to 288 plus and minus 2.776 times 4.637. If we multiply our critical t-score times the standard error of the mean, we get our 95% confidence interval is equal to 288 plus and minus 12.872. Solving for that plus and minus 12.872 gives us a lower and upper bounds for the 95% confidence interval, which are 275.128 as our lower bound and 300.872 as our upper bound. And notice that format of listing the lower and upper bounds of the confidence interval in brackets. Nice, right? Now, finally, see how this agrees with our p-value and our decision to reject or fail to reject the null. The confidence interval ranges from 275 up to 300.872. We're confident that the true mean in the population is somewhere in that range. Anywhere in that range are plausible, believable values where we think we will see the true population value. But notice that 300, the mean if the null hypothesis is true, lies in that range, in our confidence interval. So how can I reject the null when the confidence interval tells me that the null value is one of the possible values I would expect to see? How can I reject the null? It's right there. It's in the range where I think our believable population means. How can I say it's not plausible? How can I reject the null? Right? I can't. So see, the two approaches end up agreeing. With our p-value, we saw the p-value was greater than 0.05, and I failed to reject the null hypothesis because of it. At the same time, my 95% confidence interval contains the null value, which tells me I shouldn't be rejecting the null hypothesis, should I? Both approaches are consistent with each other. They both lead us to the same conclusions. Nice. And with that, let's wrap up this practice problem. This took a little longer, a little more time than you may need when you do this on your own, but I wanted to walk you through each of the steps and talk a little bit about some of the important points that come up along the way. All right? Well, I hope you found this useful. All right? Take care. See you later.